of the Arabic numerals. I know Glenn sent me an implementation, and I wanted to see what other people experience was.
Sure. So I'm not quite happy with my solution yet, but the way that I started to break it down was by defining sort of three separate grammars. The first grammar being just that you could write a single digit, and each of those cases being a pretty simple production. And then at the next level, being able to concatenate multiple digits together. So it was a grammar that was parametric in the first grammar, and you know would maybe be able to take number systems that were unary, binary, all the way up to the decimal numbers. And then level above that was addition of multiple numbers, with reductions being a reduction of two additions. But then I had to pass essentially back down through the stack a requirement of you know, implementing addition on just the grammar that has that just has you know, a single digit, and that was, you know, sort of modular arithmetic, and then up at the next level use the modular arithmetic below and some notion of ordering on the set that was passed in to sort of do, and some notion of what the smallest unit of value in the number set below is to you know, do overflow and carry the ones essentially. And then at the next level, that was, yeah, it was pretty clear once you had those two things.
Okay. Anyone else?
Yeah, I have implemented all-in-one grammar for all the numbers and like combining and addition. And I started with like a very simple, like direct implementation in so that addition was like it was the part of the language, part of the semantics of the grammar, and I couldn't distinguish two different structures. So I added like a richer structure for implementation. And then I found out that if I have enough structure, I can do all of this inside evaluation and not inside the language. So. And I already use existing function to combine multiple digits in one digit. So, yeah, it is not part of the implementation.
All right. Good. Anyone else? Going once? Yeah.
Greg? Well, yeah. So I figured I should start with counting, and then from counting, define adding, or counting up and counting down was my approach. Being able to increase and decrease the absolute value, and then from that I could define that, and I needed a concept of zero, so that if you wanted to add, you had to count up and count down to zero in terms of the amount you're adding. So you take away from one and add it to the other. Was a transfer type of approach. Anyway, I'm still thinking of how to express that as in the different tools that we've been learning here.
Right, exactly. So does anyone remember the grammar that I presented just for a monoid?
Can't say that I do.
Okay, all right. So I'm driving over to our house right now, but I'll just do it off the top of my head, and maybe someone could be a volunteer to be a scribe.
Yeah, sure. I'll be taking notes.
Okay, cool. All right. So the grammar looks like this. We have m and n are of the form. So that's m comma n colon colon equals, and then the whatever the monoid identity element is. So in this case, I'll call it 0 just for simplicity, but normally I call it e. So 0 or one of the generators of the monoid. So this will be G1 through G, N, and then so just for simplicity, let's do it this way. It's 0 or G, and we'll figure out what G is in a minute, and that fits with Jake's idea of parameterizing these things. And or we have m plus n, where the plus is the binary operation of the monoid. So that's the basic structure of the monoid. And then we have a couple of structural equivalence relations. So the first structural equivalence relation is that m plus 0 equals m equals 0 plus m. And then the other structural equivalence relation is m1 plus open paren m2 plus m3 is equal to open paren m1 plus m2 close paren plus m3. So that's the associativity, identity, and associativity rules. Now, if we're really, really careful and we do what Jake had suggested, which is we make these things parametric, then we would make m and n be parametric in G. And that's very useful. The reason that's useful is because what we really have are two monoids. The first monoid is the monoid that arises from string concatenation. And the generators, so it's just literally putting two things next to each other. And the generators are the digits of the Arabic numerals. That's going to give us a set of words. Now, the one thing that we want to do is to get rid of all of the leading zeros. So you want to make your monoid a little bit more sophisticated, so that you don't add leading zeros. And I'll leave it as an exercise for you guys to figure out how you might do that. But with that little extra detail sort of pushed to the side for a minute, we can think of the first monoid as all the strings in the with the digits of the Arabic numerals, and that monoid becomes the generators for the second monoid, which is all the arithmetic addition expressions. So let me just stop there and see if that makes sense.
It does. I guess the one thing that this strategy of removing the zeros wouldn't work for, though, is if you were doing something in unary.
Yeah, right. But I said Arabic numerals.
Right. Yeah.
Okay, so yes, that's correct. So we're, go ahead.
When is the correct time to remove zero? On the language part, on interpretation part?
Oh, that is a brilliant question. I love that question. So that's a design choice, and there are different consequences for that design choice. For me, I like to have the syntax as constrained as possible.
Okay.
So I try to keep try to keep the syntax as close to my domain as possible, so that my semantic calculations are genuinely semantic calculations and not cleaning up the syntax. But that's a really, really good observation. Okay,
because I wanted to move everything in interpretation, evaluation part. So
yeah.
Okay.
Yeah, I understood. I saw that impulse in your in your presentation, and I'm glad you're bringing it up.
Okay.
Yeah. So yeah. And this has to do with the idea of type checking. So syntax checking and type checking are the same thing. They're just at different levels. And that's something I've been trying to get across as much as possible. And it's going to be important if you want to understand the row calculus and space construction, which is where we're headed in some sense, right? So part of the aim of this course is to make sure that you guys can design these calculi, which means you understand what it means to come up with a grammar and what it means to come up with an operational semantics that uses elements of that grammar. So that's why we're kind of going through this exercise, and we should probably do 10 more of these. So now that we have two monoids, we have the monoid of the string formation, and we have the monoid of forming arithmetic addition expressions. We can now do an operational semantics, and the operational semantics, I mean, you can kind of cheat, right? Because if we assume a semantic function called addition, let's say add, okay? Then what you would do, and let's say it takes it takes the generators from the string concatenation monoid and produces the corresponding new string, and then you can always write that function in terms of the kind of standard algorithm for addition, which I think is what Jake was talking about. So then what you would do is you just have a rule that would be something like, if add of so you want to do the base case, right? So what's the base case in this case? So under the assumption that add of G1 and G2 is G3, so that would be your hypothesis. Then G1, then the expression G1 plus G2 reduces, so you have an arrow there, to add to G3, right? And then you would have a rule for the associativity, right? So you'd have a rule M1 plus M2 plus M3. So M1 plus open paren M2 plus M3. So is the case you want to consider. So this is just like the par rule, right? So you'd say that if you know that M2 plus M3 goes to M4, then you know that M1 plus open paren M2 plus M3 close paren goes to M1 plus M4. Does that make sense? Can you guys visualize that rule?
Can you please repeat? I'm a little lost.
Yeah, okay, great. So I like to do all this stuff in my head, but let me, instead of doing it in my head, I'll log in and type it in. Okay.
Okay, thanks.
Sure. Shoot, and I forgot to bring my laptop, which it had the slides on it. I might have to drive back over. Hang on. There we go. Okay, so okay, here we go. And here we go. So is it 252.216.138.1? All right. Now let me quickly leave from this device. Oh, no. Are you guys getting any echo?
Nope, not too bad.
No, it's good.
Okay, good. Awesome. All right. So here's, let me type in. So we have okay, so now I'll do a screen share. Okay, so under the assumption that G1 plus G2, so this is a different plus. Sorry, let me do, oh, sorry, there we go. Under the assumption that add of, I guess we can do it this way. Let's just do G1. I really don't like omnigraphal. Plus, sorry. Yeah, G1 plus G2 goes to, and I'll just do it this way because I haven't got this machine set up with all the favorites and everything. Goes to add, so this is the generators, right? Okay, so that's our base case. And we know that add is a built-in function that's using the strings. And then we need another rule. So this one, you know, it doesn't have a hypothesis. The other one, I'll instead of doing the above and below, I do it to the left of a double arrow. Okay, so under the assumption that M1, I did it in a different order before, but I'll do it this way. M1 plus M2 goes to M3, or no, let's say goes to M. Then we get to conclude that M1 plus M2 plus M3 goes to M plus M3, right? So this is just like the par rule in the row calc, right? So here's P reducing to P prime, then P par P Q goes to P prime par Q. It's the exact same rule. Right, and then so now that we've got it typed out, let's go ahead and do the rest of it. So we have our first, so our generic monoid, and the reason I'm doing it this way is to show that we can factor our code nicely. So we have generally M comma N. And in fact, let's do it this way. Here, I'll do it in caps just for fun. So we go M parametric in a G,
comma, in parametric in a G is of the form, either it's the identity or it's a G or it's an M plus, sorry, still getting used to this keyboard. Okay. Parametric in a G plus in parametric in a G. All right, there's our sort of overarching monoid syntax. Now notice that this plus is an abstract plus. So just for grins, not to have it collide with this one, I'll use something else, like a wow, that's not very helpful.
I think you can search for plus.
Well, I don't want plus. It's no longer. That's really okay. We'll do this one. Okay, so that's what I want. Yeah. So, doesn't want to put it in there. All right, fine. Well, we can accommodate that. We'll do it that way. That's still less convincing. How about we do this? Okay, so there's our abstract operator, of which plus is an instance and string concatenation is another instance, right? And then we have a pair of equations, right? Which is that 0 at mg is equal to mg, which is equal to mg at 0, right? And then we have the other equation, which is that so now I need instances, so I'm gonna write it slightly differently, right? I'm gonna write it like this: m1 at m2 at m3 equal to m1 at m2 at m3. Okay, so there's our generic monoid, and now we have two monoids, right? We have the monoid of string concatenation and the monoid of arithmetic expressions, right? Which in this case, we're just doing addition expressions, right? And then we compose them by making the strings be the G of the addition expressions. Does that make sense? People following along? And then
Yes.
And then we have the reduction. So then we define this add function in the carry style that Jake was talking about for the string concatenation. And then this is our operational semantics for the arithmetic expressions. So that gives us a little addition machine, right? So that's a rough shape for the solution. It's always good to go back and make sure you guys really understand it by just filling in the dots. So Glenn, this is what I'm talking about when I was talking so you submitted last night some F# code, and what I was saying was give an SOS style presentation. So what do I mean in general by an SOS style presentation? So SOS means structured operational semantics, and that presentation style was given by Gordon Plotkin. So I encourage everyone to look up SOS and Gordon Plotkin and his notes on this. Typically, instead of writing the double arrow, he would write it like this. And you've seen me do this before. So we get rid of this. And there's a so that would be the sort of style. So you write it as a rule with a set of hypotheses and a consequent. And then there are format rules as to what's a legal hypothesis. So that's really so that's one of the things that is slightly different in terms of the format you might see with an SOS style. I just use the double and then the single arrow for the reduction relation. So the double arrow is this bar here, and then the single arrow is the reduction relation. So anyway, again, you have a grammar, you have a set of relations or structural equivalents, and then you have some rewrite rules. I'll get rid of this so things are nice and clear. And then we've done one extra factoring step that is not typical for these presentations, which is that we've allowed the grammar to be parametric in something. And that comes from this observation that I just made before, which is that grammars and types are the same thing. So parsing and type checking are the same thing. That's something that's really important to internalize. Grammars and types are the same thing. And you should go and check for yourself that makes sense. And it's really interesting because that observation is a part of the folklore of a tiny sliver of the computer science community. But no one has bothered to go back and sort of rectify all of the parsing work with all of the type work. All right, so there's a whole bunch of conceptual cleanup that needs to be done, like once you make this observation, but nobody's done that, right? So if you're approaching computer science and you learn about parsing, nobody ever says, oh, hey, there's this other thing called type checking we should take a look at. And likewise, when you're reading all about types, nobody says, oh, there's this other thing called parsing that you should take a look at. They're literally the same.
When you say the tiny sliver of literature, what is that tiny sliver? Is there names?
So I said tiny sliver of folklore.
Okay, got it.
Yeah. So there's a lot of knowledge that hangs out in communities as folklore that doesn't ever get written up. Okay, so these factorization kinds of tricks are really important if we're thinking about both the mathematics and reducing the mathematics to code. And the reason, the motivation in this class, I mean, the reason we're doing it is because if you recall, I began by talking about these grammars as related to domain equations. So the domain equations are important because they give us constraints on what you can write here, right? What grammars are legal. And let me give you an example of one that is not legal. So let me. So here's a domain equation, which you can't really turn into a grammar because it's not legal. So x is equal to the power set of x. That's not soluble. Can't write down a solution to that domain equation. So it's empty. You could fix it if you just did this. So that gets you off the ground. Now you have a ground, right? So with x equal to the power set of x, you have no way, you have nothing to start with. Whereas here, at least you have, you know, I guess you have the trivial solution, but that's it. You have x, the empty set, but that's the only solution you can get. Here, we know that that is 1, and so we can do the power set of that, right? Which would be the empty set, right? And so on, right? So you see that now you can start, now you can get off the ground, right? So that's how you this is well formed. There's a wonderful book by John Barwise called Vicious Circles, where he talks about kind of soluble domain equations. The reason I'm interested in this is, and the reason I'm trying to, what I'm trying to do is to motivate something. And what I'm trying to motivate is that all the grammars are related to monads. And in particular, they're going to be very, very nice monads. Now, the way in which the grammars correspond to monads is identified in category theory via Levier theories. So we don't have time to talk about, to unpack Levier theories much in this, is because it's a little bit out of focus. But I heartily recommend that you go look at the relationship between monads and Levier theories. And this is very, very important if you want to understand the ladle construction. But for us, what we can simply say is that the grammar is going to give is going to be isomorphic to the to a different presentation, which is a monad. So it's a particular kind of type. Now, for our purposes, you can think of a monad as a parametric type. Okay, so it comes with 3 things: shape, which is the type constructor, and it's a parametric type constructor, and wrap. So I need a function called wrap. I don't want you to capitalize every time I write things. Not helpful. And wrap goes from x to t of x. Right? And notice that if I have a function like this, then since and I get to be, just to be super careful about this, it's parametric here. Okay, so since it's parametric there, I get to have an instance of wrap, which is the t of x. So that would go from what? From what to what?
T of x.
Ax.
Keep going. T of x to
TTX.
Yes, T of X to TTX. Exactly. Okay. And you're off to the races, right? So you go from Tn to Tn plus 1. So what wrap really does is it gives you a nesting function. It shows you how to nest t's. So if t is your shape, wrap is how to nest things inside the shape. Okay, and then since we can nest, we'd like to be able to flatten the nested structures. So I call that roll, as in rolling up. So we have shape, wrap, and roll. Okay, so roll is also parametric in an X, and it goes from a T of X to a T of X. So it flattens things out. So that's our basic monad, and there's some coherence laws about how wrap and roll have to interact with each other. And I heartily recommend that you go and look at the literature on monads and how this is typically called the unit, and this is typically called the mult. And the reason they're given those names is because there's a strong relationship between our monoids and our monads. They're essentially the same object. When you parameterize your monoids in the way that we did here, you get a monad. So that gives you a hint or a clue as to what's going on with these Levier theories and how you might get a relationship between types and grammars in the way that Levier did with the monads. Okay, so with that, we can now look at something that's very, very important, and that is the notion of a derivative. Let's see if I can do this. Yes. So if I have certain types, I can form a derivative. And what this really is it has to do with so how do I say this? Remember, we talked about the relationship between the domain equations and types. We introduced sums and products. So you know, like we just wrote down an expression like 1 plus how of x, right? More generally, and then in our other examples, we wrote down, for example, the domain equation for the lambda calculus, and we use products as well as sums, right? So the domain equation for the lambda calculus was T of x is going to be equal to, so x is our set of names. So either you can mention a name, or you can have a name together with a T of x. So that's abstraction. Or you can have an application. So this would be T of x cross, T of x. So there's our domain equation, right? And this is just like a type, right? And we talked about that in the beginning of these courses. Now we can take the derivative. If I get rid of the x's for a minute, if I do something like this, let's just take this out just for a moment. So we understand that t is a kind of recursion variable. Then I could take the derivative with respect to t. And the derivative with respect to t is going to be calculated in just exactly the way we calculate the ordinary calculus derivative. Oops. Whoa. So when I get to something that's not a variable, so x will just go away. With respect to the derivative, with respect to t, x is a constant, so the derivative of a constant is 0, so it makes no contribution. And the derivative of a product, right, is just going to be just the constant, right? So the derivative of the second term is just the constant, right? So the derivative of sums just sprinkles the derivative across the sums. So it distributes the derivative across the sums. We get nothing from here. We get just the x from here. And we get, what do we get here? We get t plus the derivative of t, right? There it is. Whoops, that's weird. Why is that happening? Oh, I see what happened. Sorry. We can defeat this. There. Derivative of t. Sorry, this should be times. Oh, I see what's going on. That's weird. So that's the usual product rule. And I've sort of, we can go over the recursion, but that's less important. The more important thing to note is that if we look at the contexts for the lambda calculus, what are the contexts for the lambda calculus? So remember how we built the context for the row calculus. We can do a similar kind of thing. We also mentioned that contexts are important in doing Morris-style equivalence for the lambda calculus. So the context for the lambda calculus would be of the form, well, we want an abstraction context, right? So we start off with a whole, and in fact, we could even, yeah. So derivative of t with respect to t is just 1. And the derivative of t with respect to t is just 1, right? Cool. So we start off with a whole, and then we either have abstraction, and sorry, this should be cross 1. So we have abstraction, so that would be lambda. I'll write it Haskell style so I don't have to go searching for the lambda. So this would be lambda x arrow k, and then we have similarly a lambda term cross a context, or a lambda context cross a lambda term. So that's the, so now if you look, these shapes line up exactly. So there's our lambda term abstraction with a context. There's our term in a context. There's our context in a term. Now, I haven't done the most convincing job because I just did it off the top of my head. Perhaps next time I'll have it all written up for you. But what you should know is just that the calculation of the derivative is exactly the formation of contexts. And so that's the thing to take away. So most people, so in the beginning, people would define contexts by hand. And then later, Connor McBride discovered that there was the notion of a derivative of a type, and what it gave you was the one-hold context. And this is really, really important because now when we want to refer to one-hold context, we can just simply talk about them in terms of the type itself via the derivative. And that's really, really important because the next step in this process, here, so let me get rid of this. The next step in this process is that we want to define a location. So a location, here, let me see if I can draw it first. We can think about it generally. Let me go get a stencil here. Okay. So let's take a look just at the notion of a tree. So let's just look maybe at a binary tree for a minute. All right, and then just for fun, oops. And then why would we do that? There we go. Okay, so there's a binary tree, and let's say that we wanted to locate this node. Is there a way that we could do this generic? And in particular, the reason this idea of the zipper was originally formulated was because when you make data structures like binary trees and you try to do operations like changing values at nodes or restructuring their tree in some way, if you do it in an immutable style, you end up copying everything. Right? And that's a problem because it's not very efficient. But if we could provide a notion of location, then we could do mutation and navigation operations in a much more efficient way. So if a French computer scientist whose name I will butcher, but I pronounce it Huet. It's Huet. Came up with this structure, but it was later discovered that the derivative gives you this information quite generically. So to describe this location, what we'll, hang on a second, let's see if I can do it this way. We break this up into two pieces. And this part, let's see. Let me, so I'm going to represent a tree context like this, right? So here is a tree with a hole in it. And it's a lot like the lambda calculus term, right? Where the application structure, right? The application, which is very much like the monoid construction. We have a left part and a right part, right? So that's why I use binary trees, right? If you go back here, right, you see we have a left part and a right part. And this looks just like a binary tree, yeah? So I've basically got binary trees inside monoid constructions. So that's why I'm using the binary tree as my example. So here I've got the left part of my application and a hole. And over here, this is something that I could put into the hole. Oops. See if I can do that again. So this is something I could put into the hole, filling the hole. If I make the hole big enough. Maybe, oh yeah, it's because of the way I've done this. So let's do it that way. And then not that, but that. Oops. Not that. Ah, one more time. But not that. There we go. So this fills the hole, and so that really points to that. But OmniGraffle is going to complain about that. But hopefully you see the idea. So now, when I have a context plus the thing that fills the hole, that can describe this location. And notice that it's not sufficient just to have the thing that fills the hole, because I could put it in lots of contexts. And notice it's not sufficient to have the context because I could put lots of things in the hole. Only both pieces of information give you the location. Is everyone following? Okay, all right, so let's see if I can. Wow, this is annoying. The mouse doesn't want to give me the usual navigation. I can go, but how do I go up and down? All right, we'll just get a new canvas. Okay, so if I just go up to here and then grab this. So now what we're saying is that the location, possibly the location of T, so T is our monad, is going to be a pair, which is the derivative of T, together with an instance of T. That's our location. Is that making sense? Cool. Now we can use the trick that we used with the row calculus. Okay, so the trick that we used with the row calculus was to parameterize the notion of names. in terms of the terms themselves. But now what we want is we want names to be the locations in terms. This is really, really a little bit mind-bending. So names are going to be not terms themselves, but locations in terms. So remember, our row calculus expression, so R of X, whatever it is, so we're not gonna close it up just yet, right? So we have the 0, and then we have the for comprehension, which I'll just write this way. So it's R, so it's X cross X cross R of X, right? And then we have X cross R of X, right? And then we have R of X cross R of X, that's par. And then finally, we have an X, right? And that's eval, just an X. Right, so that's the 0 that gets us off the ground. That's our for comprehension. That's our output. That's our par, and that's our eval. Okay, so now what we want to do is to make a new calculus where the calculus is instantiated. So we'll call it L of R, or just LR because I need to. Okay, and this is going to be R in which I give the names in terms of its lock of LR, where lock is this thing. So we can actually instantiate this, right? This is equal to R of the derivative of LR paired up with LR. So we have Casper in just 1 minute here. So I'm gonna have to jump off. But this is, I wanted people to have a sense or a taste of where we're headed. Okay, so we went kind of, what we did in the last exercise in this one was to show that we could do fairly low-level stuff like addition. But if we treated our low-level stuff appropriately abstractly, which is what's going on here, we can get a whole bunch of factoring techniques for our presentations. So we can do lots and lots of things, right? I was relating addition to par here, right? So it's the same set of techniques, even though we're doing something as low level as addition. And the reason this is important is because once we recognize that the grammars are in fact types, then we can employ all the power of types. And in particular, what we can employ as an example is the derivative that we can take on types. And then this gives us the ability to utilize that in our recursion. Now, I just want to say that just because we have a domain equation doesn't mean we know what the solution looks like. I intuited this domain equation in 2008 on a cold, wintry, snowy night driving from Seattle to Vancouver. And it took me until 2018 to write down the solution to this domain equation. And so what I'm going to do is present the solution to this domain equation at the end of this, but I want people to see where we're headed. It's a very easy domain equation to write down, right? This is a tiny, tiny little domain equation. In fact, if I get rid of this part here, this is how small it is. There, that's the domain equation. But providing the solution in a way that makes sense relative to the operational semantics turned out to be much more complicated. So we'll unpack that by the end of the course. So thanks very much. Looking forward to talking to you guys next week. And yeah, have fun.
Thanks.